Okay, Pre-Cal 11, here we go. We are going to look at our exponent and radical refreshers. Some of these laws will be new, some of these laws will be old, some of these laws might seem new, but they are old. It's all good times. So, quick recap of something that you'll see sparingly, but if you have a negative base and no brackets, this will always be negative because that negative is a -1 and the exponent is not acting on it. But if you ever see yourself with a negative number in brackets, the exponent now matters because this is a negative number multiplied an odd amount of times, which will always result in a negative answer. And this is a negative number multiplied an even number of times, which will always result in a positive answer. So just be aware of that. You'll see it sparingly, but it's really important feature and a really important aspect of exponents. So now let's jump to the rules we learned. First one is multiplying a common base, and it's important that the base is common. So that means you have, for instance, 2 to the power of 3 times 2 to the power of 4. We add those exponents, 2 to the power of 7. If you have x to the power of 2 times x to the power of 9, well, x is a common base, so you have x to the power of 11. That's the multiplication principle. We have a common base, we add the exponents, quite straightforward. Division is also quite straightforward. If we have 7 to the power of 7 and we divide 7 by the power of 3, common base, so we subtract our exponents. And again, you could have a variable, so t to the 7 over t to the 2, and you get t to the 5. Now in a minute, we're going to look at negative exponents, so just be aware of those in this process as well. If we come back to multiplication, you could have x to the -7 times x to the 9. Well, you add those up, you're still going to end up with x to the 2. And here's where you really want to be careful. If you have, let's go 2 to the 3 over 2 to the -5, well, 3 minus -5 is 3 plus 5, so you'd end up with 2 to the 8. So be aware of those negative numbers. It comes back all the way back to probably the first lesson in grade 9 about integers. We want to make sure we are adding and subtracting them accurately. So the next one is a zero power and negative exponents. We can actually prove both of these using the rules we just looked at. So 5 to the 0, we can agree is 5 to the, and I'm making these ones 3 minus 3, right? Because 3 minus 3 is 0. And if we subtract a common base, it's because we were dividing that base. And anything divided by itself is a 1. So since all of these statements are equal to each other, we've proven that anything to the power of 0 is equal to 1. The only place you need to be careful is a minor caveat if you're dealing with variables. Now variables, that's still true. It's 1, so t to the 0 is 1, but the only thing is here, t would not be allowed to be 0 because you can't divide by 0. So when you have a variable, you have a minor caveat where you have to say t is anything except 0, otherwise the system breaks down. But anything to the power of 0 is equal to 1. And now negative exponents we can prove in a similar fashion because 5 to the -3, well, we should be able to agree that that's the same as 0 minus 3, which means we have 5 to the 0 over 5 to the 3, and we just proved that 5 to the 0 is 1, so we have that. So what that means is when you have a negative exponent in the numerator, it just goes to the denominator and the exponent changes positive. Now to build off of that, if you already have a negative exponent in the denominator, well, guess what? It just goes up to the numerator, and that's because of fraction rules, because technically you would now have that. So rather than worry about the complicated view of that, just know that if it's negative here, it ends up here, and if it's negative up top, it ends up in the bottom. Now, power to a power is when we have things like 2 to the power of 2, all to the power of 3. In that scenario, we multiply our exponents. But you could also have something like 2 over 3, let's say 2 and 3 to the power of 2. Well, this has to multiply into there, and it has to multiply down into there. So you have 2 to the 4 over 3 to the 12. So just be aware, you can have a fraction for sure. Now things are going to get a little bit more complicated. You could have something that looks like this, 2 to the power of 2 over 3 to the power of 3, but let's say it's all to the power of -2. Well, you have two options. You could multiply that in, and you'd have 2 to the -4 over 3 to the -12, or sorry, -6. But then you'd have negative exponents, so the numerator would go to the denominator, so the 2 to the 4 would end up down here. And since you have a negative in the denominator, it would go to the numerator, so it would end up here. So that's one way. But the other way is if you have a fraction with a negative outer exponent, you can just flip the inside first, change the exponent positive, because you'll see we end up with the exact same solution. So be aware, you can handle these in a number of different ways. Do whichever way you feel the most comfortable with and allows you to work through these questions with the fewest number of errors. That's obviously important. So let's look at one that kind of involves everything we just talked about. So I'm going to start by multiplying my exponent on the outside and doing my power to a power. So that's going to go in there, in there, in there. So I'm going to end up with 2 to the negative 2, a to the negative 4, and b to the negative 6. And then I'm going to multiply this in there, in there, in there. And I'm going to end up with 4 to the 3, a to the 3, b to the negative 3. And then on the bottom, I'm going to do the same, and I'm going to end up with a to the negative 12 and b to the negative 4. Now, very helpful to notice that 4 can be written as 2 to the power of 2, and 2 to the power of 2 then cubed is 2 to the power of 6. Now, this is helpful because what you can do is you can change the 4 so you have a common base. Now, this isn't necessary, but it's incredibly helpful. So I'm going to go 2 to the negative 2, so this one. And then I'm going to write my next 2, but 4 to the 3 is actually just 2 to the 6. And then I'm going to compute my variables. So I have a to the negative 4 and a to the positive 3, which is going to give me a to the negative 1. And then I have b to the negative 6 and b to the negative 3, which is going to give me b to the negative 9. And on the bottom, I have my a to the negative 12 and my b to the negative 4. There's nothing I can do there. But now you'll notice I can combine those 2's. So I end up with 2 to the 4. And then I will do my division of a common base. And here's where you're going to be careful. Negative 1 minus negative 12 means negative 1 plus 12. So I have a to the 11. And then negative 9 minus negative 4 is negative 9 plus 4. So I have b to the negative 5. And now the last step, if this number is manageable, right? If this number is like 81 to the power of 7, well, you don't want to write that down. It's going to be huge, so you just leave it there. But 2 to the power of 4 is 16. And then the a to the 11 stays where it is, but the b to the 5 goes down to the denominator. And that is your solution for that one. So multi-step, multi-pronged. You can actually tackle this in a number of different ways, but this is the way I would recommend. At least until you get really comfortable. Now, here, I notice I have a 3 and I have a 2. And here I have a 9 and I have an 8. So I'm actually going to deal with that first because I know that 9 is 3 squared and I know that 8 is 2 cubed. And what that does is it gives me a common base for all of my coefficients. So I'm going to rewrite this as 3 squared and then a b to the negative 1 over 2 cubed, a to the negative 2, b to the 2, all over negative 2, or all to the power of negative 2, and then 3, a to the negative 2, b to the 2, over 2a squared, b to the negative 1, all to the power of 3. So bear with me, make sure I don't make any mistakes here, okay? Because here's we're going to do a lot of power to a powering. This has to go into everything top and bottom. So I'm going to have 3 to the negative 4. I'm going to have a to the negative 2, and I'm going to have b to the positive 2. And in the denominator, I'm going to have 2 to the negative 6, but then I'm going to have a to the positive 4 and b to the negative 4. And now for my second one, I'm going to have 3 cubed, a to the negative 6, b to the 6, over 2 cubed, a to the 6, and b to the negative 3. Now, you have two options. I'm going to show you the first one going to the right. And for the first one, I'm going to multiply my tops with my tops. So I have 3 to the negative 4 times 3 cubed is 3 to the negative 1. I have a to the negative 2 times a to the negative 6 gives me a to the negative 8. And then I have b squared times b to the 6, which gives me b to the 8. So there's my start. And then on the bottom, I have 2 to the negative 6 times 2 to the negative 3, which gives me 2 to the positive 3, which gives me 2 to the negative 3. A to the 4 times a to the 6 gives me a to the 10. And then I have b to the negative 4 times b to the negative 3, which gives me b to the negative 7. So now I will do my negatives and my division. So 3 and 2 are different bases, but they have negative exponents. So what I can do is I can swap them. And I'm going to have 2 cubed up here. I'm going to have 3 to the 1 on the bottom. And now 8, a to the negative 8 divided by a to the 10 gives me a to the negative 18. And then b to the 8 divided by b to the negative 7 gives me b to the 15, because I'm doing 8 minus negative 7. And the only thing we'd have to fix here is now 2 to the 3, well, that's a manageable number, is 8. The b stays up top, and then the 18, a to the 18 ends up on the bottom. Now that was doing the multiplication first. I will show you just below, you can do the division first, right? You can divide the common bases here and here, but you can't do anything with the 3's. So what you would have is you would have 3 to the negative 4, and then a to the negative 6, because we're dividing a common base, and then b to the 6. But this 2 to the negative 6 would just be hanging out on the bottom, because we haven't done anything to that yet. And then you'd have 3 to the 3, but then you'd have a to the negative 12, and b to the 9. And this 2 would still be hanging out on the bottom. And then you would do the multiplication step, and you'd end up with the 3 to the negative 1, the a to the negative 18, the b to the 15, all over 2 to the negative 3, and then you'll notice we end up right back there. So I just showed you 2 quick differences in method, but you should end up in the same place in the end. Okay, so now we already spoke about this one, but if you have a negative and it goes into here and into here, it has to do both. And then from there, those would swap positions. So just to reiterate that piece, very, very important one there. You could also swap that first and just change that exponent positive, because it has the same net effect, right there. Now, here's something that might be a little new to you, rational exponents. And I just want you to consider that 4 squared is 16, and that the square root of 16 is 4. And that square-square root relationship demonstrates that if I had the square root of 16 and I wrote it as the square root of 4 squared, well, I get the same answer, obviously, because 4 squared is 16. So it says that there's a relationship between the squared and the square root, and that relationship cancels out, and it would leave us with an exponent of 1. So from that logic, the square root symbol must represent an exponent of a half. And that's the relationship. Whatever this bottom number is, represents the root index of your radical, and the top number is your power. So x to the 1/3 is the same as the cube root of x. X to the 1/4 would be the 4th root of x. X to the 1/2, well, that's just the square root of x. So that's the relationship between a rational exponent and its base. Now, obviously things are going to get a little bit more complicated, but we'll look at a couple examples here first. So if I had to multiply these things together, well, I have a square root and a 4th root, so different index of my root, right? So this is 1, not 1, this is 2 to the 1/2 times 2 to the 1/4. But now that you see them as exponents, you can get a common denominator. So that's the same as 2 to the 2/4 times 2 to the 1/4. And now you can combine them because, yes, you have a common base, but you also have a common denominator in your exponents. So you have 2 to the 3/4. I'll show you how to simplify that on the next slide. Now, the next one we have, well, this time we have 2 to the 1/2 times 2 to the 3rd times 2 to the 6th. Well, if we get a common denominator, we have 2 to the 3/6 times 2 to the 2/6 times 2 to the 1, which gives us in the end 2 to the 6/6. And this is easier to simplify because it's just 2. So just identify that relationship between the index of the root and the denominator of the radical exponent. Because from there, we're going to jump it up a little bit to this idea. Now, for this one, I like to draw a little picture of a plant. And for the plant, what's in the bottom? Well, the roots. And then you have the stem, the leaves, whatever you need. And then at the top of that plant, you have your flower. So, flowers at the top, roots are at the bottom. Now, the roots just stare you in the face, but flower rhymes with power. So that means in a rational exponent where you have a numerator, that's at the top. That's your flower, so that's your power, and that's your root. Now, if you think about this as a power to a power multiplication, well, that means you had that, or you had that, because if you multiplied those exponents together, you get 4 over 3. So what that tells us then is that tells us that this is written either as the cube root of 8 to the 4 or the cube root of 8 all to the 4. They're interchangeable, they're exactly the same. This one's easier to use because you can simplify it easier. Because what's the cube root of 8? The cube root of 8 is 2, so it means you have 2 to the power of 4. In this example, you would have had to calculate 8 to the power of 4, which is a relatively large number, and then try to find the cube root of that relatively large number. So a lot more work. So this notation is a lot more friendly to you. So just remember flower, power. Let's look at a couple examples. So how do I simplify these? Well, here I have 4 to the 3 halves, which means I have the square root of 4 cubed, because that's my root and that's my power. And you'll notice here it's helpful because now I can square root 4 and I just get 2. 2 cubed is 8. Done. Now here I don't need to convert into an exponent because I already have it broken down as a roots scenario, but remember that that's going to be the same then as 32 to the 4 because that's my flower power and my root, right? So now the fifth root of 32, well, 32 is 4 times 8. 4 is 2 times 2, 8 is 2 times 4, 4 is 2 times 2. Would you look at that? I have 1, 2, 3, 4, 5 2's. So it means the fifth root of 32 is 2. And then I have 2 to the 4, which in this case simplifies to 16. Now here, we're going to have the same scenario, but you have a negative. But remember, let's just deal with that first. A negative exponent ends up in the denominator and becomes positive. And then from there, everything stays the same. So we have the fourth root of 16 cubed. The fourth root of 16 is 2. So 1 over 2 cubed. And 2 cubed is just 8. 1 over 8. So they all simplify out. The more practice, the easier it comes, the more straightforward it comes, the steps will just begin to flow. So a couple more things. How do we simplify these things? Because you'll notice that's not the same as that. Well, let's just take this one step at a time. Let's first convert these into rational exponents. So this is 4 to the 1/3, and this is 2 to the 1/4. So I can't do anything right now because I don't have a common base, but remember that 4 is 2 squared. So now I actually have this over this. And now I can go power to a power here, and I end up with 2 to the 2/3 over 2 to the 1/4. And now I get a common denominator, which is 12. So 2 to the 8 over 12 over 2 to the 3 over 12. And now I can just subtract my exponents because I have a common base and I have a common denominator. And I end up with 2 to the 5/12. Now there's nothing we can do from there. I'll show you how to convert things like that. If we wanted to, we could convert that into the 12th root of 2 to the 5, but honestly, this looks better. Now let's look at this last one, 9. Well, I recognize 9 and 27 right away. 9 is 3 squared, 27 is 3 cubed, so I'm going to go from there. So if I flower power this thing, the cube root of 9 is the same as the cube root of 3 squared, and the fourth root of 27 is the same as the fourth root of 3 cubed. So I'm going to convert this into 3 to the 2/3 times 3 to the 3/4. Now I have a common base, but I need a common denominator. So again, it's 12. So I have 3 to the 8 over 12 times 3 to the 9 over 12, which now I can add my exponents. I get 3 to the 17 over 12. Now, your brain might be going, okay, great, I got the hang of this. Now this is going to be the 12th root of 3 to the 17. Sure, but I'm going to show you next video how to simplify this, but actually do a little spoiler here, a little teaser. 17 over 12, well, that's the same as 12 over 12 and 5 over 12, because if I added those exponents, and I only picked this because 12 over 12 is 1. So this is going to simplify to 3 times the 12th root of 3 to the 5. But we'll look at that in the next video. So there is a refresh slash renew slash new information slash, oh my God, there's so much going on here. What am I going to do? So maybe watch this a couple times. If you have specific questions, drop a comment. I'd be happy to do a little short video for you. Thanks so much. Thanks for watching, and I'll see you next time.